talk about was the size of atoms and ions. And we have to be very careful when we think about what we're talking about, okay? So for example, if we're looking at, let's say, sodium right there on the table, okay? We recognize that when we're talking about the size of a sodium atom, we're really talking about the metallic radius, okay? We could make a diameter out of that, but it's all the same, okay? So we really recognize that we're talking about how sodium exists as a metal, okay? Similarly, if let's say we were talking about chlorine, if I was talking about the atomic radii of chlorine, because chlorine exists naturally as a diatom, okay, when we're talking about the size of a chlorine atom, we're really talking about its covalent radius. And we could talk about that in terms of a diameter as well. But we have to think about what state things are in on the table, okay? So we recognize chlorine exists as a gas, Cl2. Okay, sodium on the table exists as a metal. But what about now when I make a compound out of these? So when I make an actual NaCl compound out of those two things, okay? Well, we're no longer using the metallic or the covalent radius or the size of the atoms. The sizes actually change when these things become ions. So you can see chloride actually becomes bigger than what it should be as a covalent radius. And we know that sodium, you can see sodium became much smaller, okay, than it did before. And I'm going to explain that. We're going to come to that, okay? So here is the trend that we see with atomic radii. And what I want to point out, look, sodium 186 and chlorine 99, okay? Look, there it is. There's the 186 for sodium, right? And then there's the 99 for chlorine, okay? But not the 102 or the 181, all right? So what we see here is there's a general decrease as you go up, or we could say a general increase as we go down, all right? And so now, let's see here, I'm getting notifications, so I've got to put that away. Okay, so now let's see here. And so this makes sense, right? This starts with hydrogen being 1s, and hopefully you remember that when we talked about the size of these orbitals, that they get bigger, right? Those onion shells get bigger as we go down. And so when we can see that, right? If I move down a group, we can see them getting bigger, okay? So the general decrease or increase as we go up or down is because of the size of the orbitals, okay? So I'm going to write that down there. I'm going to say size of orbitals, okay? And so now there is a general decrease going this way, which seems counterintuitive. And so why is that? Well, the general decrease, right, if I pick on lithium and go across to neon, you can see the sizes are decreasing. So why is that? Well, the sizes are decreasing because of the number of protons. So what does that mean? Well, if, for example, I pick on this level 2 here, it's all in the level 2, right? The 2 sublevel, okay? N is equal to 2. As we move across, okay, the orbital is more or less the same size, and we are increasing the number of electrons as we move across. However, those electrons are within roughly the same sized shell. But what is happening is now there's more and more protons being added to the nucleus as we move across, and that causes those electrons to shrink in, okay? So this is a little counterintuitive that, that they get smaller as we move from left to right. And that's due to the number of protons, okay? To me, I think this is really makes a lot of good sense that the atoms get bigger as you go down or get smaller as you go across, okay? And so now what this means is if I try to compare like a sodium to something like tin, you know, if I'm comparing something from up here on the left, so from the top left, and I'm comparing that to something on the bottom right, that becomes really difficult to make that comparison, okay? So you should just know the general trend, decrease up and decrease to the right, okay? So moving forward. So now what about ionic radii? So now that's related to this idea. Now when these two things become compounds, and specifically when they become ionic compounds, okay? Well, we can only compare isoelectronic ions, first of all. And so what that means is I can only compare things that have the same electron configuration. All right, so let's pick on O2 minus, F minus, Na plus, Mg2 plus, and Al3 plus. So I'm gonna circle all of those, okay? So these are all isoelectronic with neon. Yes, these are all isoelectronic with neon. So they all have the same electron configuration as neon, right? F minus, O2 minus, sodium plus, Mg2 plus, Ag3 plus, okay? We see another trend right here. I'll do that in red, okay? So I'm gonna circle this trend right here, okay? So this trend, sulfide, chloride, potassium, and calcium, these are all isoelectronic with argon. So I can make a comparison amongst that set. But I can't compare those two sets, okay? And so what we see now is O2 minus is bigger than F minus, right? 140 is bigger than 133, which is bigger than Na plus at 102, which is bigger than Mg2 plus at 72. And I ran out of room here, but finally that's bigger than Al3 plus at 54. Okay? And then notice when we get to sulfur, the trend starts back over again. And if we look at this new trend right here, look, I've got sulfide at 184, which is bigger than chloride at 181, which is bigger than potassium at 138, which is bigger than calcium, 2 plus, at 100. And then look, when I start at selenium, a new trend starts over. Okay? So what's going on with these things? And why can we only compare with isoelectronic? Well, as it turns out, it's the nuclei that's really playing a big difference here. So because these are all isoelectronic, they all have the same number of electrons. However, as we move across and then down, we have more protons in the center, and that causes these things to shrink. Okay? And you also notice here, if I compare now, let's say an oxygen to an O2 minus, you can see the anions become quite large, which is the opposite of the cations. The cations get smaller and the anions get bigger relative to their atoms. Well, why is that? Well, that's because we're adding electrons or we're taking away electrons. So in the case of the anion, when I add 2 more electrons to oxygen, those 2 electrons are repelled and interfered with by the other electrons. So they push themselves out a little bit because they're negatively charged. They don't want to be interacting with the other negatively charged oxygens, okay? So that's why the anions become a little bit bigger. Similarly, now the cations become smaller because I'm taking away an electron, and now there's less negative interference, and those remaining electrons can get sucked in by that positively charged proton, okay? Or nucleus, I should say. So keep in mind, we can only compare isoelectronic ions, but what we see with each trend is the more positive it is, the smaller it is, because the protons are sucking in those electrons, okay? The more negative it is, the bigger it is, because there's negative interferences with those electrons. All right?